Hello, everybody. Welcome back. I hope you're doing well. We are going to keep talking about drug discovery. Now, the last story that I told you before we dive into this was about Dr. Sidney Farber. He's normally called the father of chemotherapy, and that is because he came up with the first targeted chemotherapy drug that was not poison, right? So he is a hero in biochemistry, and uh, we like him. However, another hero, another favorite biochemist of mine is an Indian guy. His name is Dr. Subaro, but full name is Yela Pragada Subaro. And the reason why I like him is because we talked about how Dr. Faber targeted DHFR, right? Our favorite protein. Well, what if I told you that he is not the one who discovered the drugs, the drug that we've been talking about? It was his assistant, and his assistant was this Indian unknown biochemist not called Dr. Subaro. So this is one of those chemists or biochemists or scientists that nobody cares about, but they did a lot of stuff, right? Just like Dr. Rosalind Franklin, he did a lot of work. He's actually one of the people who came up with or who discovered the function of ATP, right? We know ATP now as the powerhouse, the molecule, the currency in the cell, the currency and the energy. But they didn't know this, and this is the guy who figured it out. But on top of that, he came up with a lot of inhibitors of DHFR, including the one that we've been looking at, which is the methotrexate, right? That is the cancer drug, the targeted cancer drug that is still being used today. So that's the fun fact that I wanted to talk to you about before we dive into this. But we have been looking at the inhibitors of DHFR. So let's look at this. All right, so this is actually one of you guys's docking result, right? So this is DHFR, and this is the molecule bound into it, right? So I just visualized it, made it look good so that you can see all the structures and all the interactions, and you can even see the hydrogen bonds and everything, right? It's really good. So yes, this binds and this binds really well, right? This is one of the biggest success cases of enzyme inhibition, right? But sometimes some of the molecules that we have are not good. They are not good. And because of that, some of the drugs that we have are not good. And we need to make some better drugs. And that is what today's class is about. It's about making better drugs based on existing drugs. And that is the core of drug discovery, at least in this class. Because if you have the protein structure and then you know the molecules that bind and where they bind, you can use that information to design better molecules that bind better. And guess what you do? You come back and target the same pocket and see if the molecules that you've designed also bind better, right? So we can do it in a computer before we do it in real life. And guess what? Because the computer does not go to sleep, you can come up with thousands of molecules and then test them, right? Because of that, people have made repositories of molecules, and we call these libraries, right? So the first lesson for today is molecule libraries, right? So there are databases, right? So the one that I'm going to start with is PubChem, right? You've seen PubChem, and I love PubChem because PubChem is a repository of all of the chemicals. It's not just the drugs, right? The poisons, you know, everything is on PubChem, right? You can find anything on PubChem here, right? You see aspirin, and all of these. And then if you click on it, it's going to tell you this should, right? As such, this is one of my favorite, one of the molecules that I work with. I just wanted to show you as an example, right? If you open it, you should be able to see anything, to see all of the information. I think I just have a slow internet, but structure, name, right? On the side here, you can see people who sell it, chemical vendors. You can see biological test results, right? If somebody has tested this on cells, on proteins, on animals, you should see it. And then it's going to also tell you whether or not it's a drug or something like that. So this is a repository of molecules. And as we talked about, we know that we need to know the language that the computers understand. So the computers are going to use the smiles, and in 3D space, they're going to use SDF. So you're gonna download the SDF file and then copy the smiles for any chemical that you have, right? But in addition to that, if you have, let's say, the smiles, right? I'm gonna copy these smiles, right? Structure, right? You can not only copy this, but if you have a molecule, right? Let's say I have a protein here and I have a molecule that binds, but it's not good. I'm like, okay, let's see if we can do better. We can copy the smiles, and then we can come here. We can paste the smiles here, right? And then you can search, right? You can search. And of course, it's going to show you the actual molecule that we found. However, it's also going to search the similarity. It has a similarity feature, right? So it's going to search similar molecules that have the same kind of structural features, same shape, right? So we're going to have a similarity search where we can download all of the molecules, by the way, all of the molecules that look like our original molecule, and we can change the settings, different type of similarity, substructure, superstructure, 3D similarity, right? 3D similarity is if the shape is actually good. Why do we want a 3D similarity? Is because we want the thing to fit in this pocket, right? So similarity search is a very, very important part of drug discovery, right? We're going to do similarity search. We can do a 2D similarity search or 3D similarity search, right? So that we can see, is it the chemicals? Is it the 2D shape? Is it the 3D shape? Is it the atoms, right? So we can search. So PubChem has millions and millions of molecules. But like I said, this has poison and real molecules, right? So there are other libraries. For example, zinc is another library. Zinc is much better because it's geared towards docking, virtue screening, and drug discovery. But look at this. It has 750 million compounds. It's crazy, right? So zinc is another database that we use. So there are so many databases. There are databases of natural compounds, databases of um, existing compounds. We have this database called the Campbell database. I like this one as well. It's a database of bioactive compounds, the compounds that we know that do something in your body, right? So we're talking about millions. So as you can see, this is smaller than PubChem and zinc, but it's much more relevant to being a drug, right? We also have some databases like this is the database from FDA. This contains a database of all of the drugs that have been discovered, right? Not discovered, but approved by FDA, right? So you can actually download it from the FDA website, and then you can use a lot of um, a lot of algorithms to search this. So we love this. We love libraries. We use a lot of libraries, but for this class, what we're gonna use is one called ChemSpace. Why? ChemSpace is like Walmart, right? So if you search something on zinc, you will find molecules. But what if you find a molecule that doesn't exist, right? You'll need somebody to make it for you because some of these are molecules that do not exist, right? It's just structures. By the way, before we go there, you can even here on in PubChem search by drawing, right? So you can draw a molecule. Let's say you have a molecule, right? You can draw it, right? I love these. You can draw exactly how you want it, right? Add, let's add a double bond just for fun. Let's add nitrogen, right? You can add nitrogen in the middle, right? You see, you can just draw it. And guess what? When you draw it, it's going to give you the smiles on the top here, and then you can accept structure, and then guess what? Search it. So you can not only search with smiles, you can actually draw it. It's telling me that it doesn't exist, but it has a lot of similar molecules. So this is similarity, right? Right. So here, go into ChemSpace. You can click on small molecules. The reason why I love ChemSpace is not a library or database. No, ChemSpace is actually a chemical vendor. Everything they show you, you'll be able to buy, right? So let's go with our molecule that we like that binds to DHFR, right? Methotrexate, right? And we're gonna search for it, right? So let's say we want molecules that are similar to this, right? We're gonna search for it. I just want the smiles here, right? Copy the smiles, go to chemical search, and then what am I going to do? I'm going to just click paste, Control V, and it goes from smile to structure. It's crazy, it's pretty cool. And this is our molecule. And I don't want to search an exact match, no, I want similarity, right? So I'm going to run similarity so that it's going to give me molecules that are similar to this. But again, the reason why we chose ChemSpace is because every molecule that I'm going to have here, I'm going to be able to buy it by click of a button. And the beauty of it is ChemSpace is not very expensive. It tells you the price here because guess what? This one is, no way, $11 for 250 milligram. But I know, never mind. I know why. This is this is the original molecule. This is methotrexate. So when it's an established drug, it's gonna be very cheap, right? But under this, then we're gonna have other drugs that are similar to it. Again, for this one is different because this drug works really well. It's already commercial, but again, it's going to give you a lot of molecules that are similar to this, right? So what we can do is from this, we can download it, right? So it's telling me that it's found like hundreds of molecules. You know what I'm going to do? I'm going to click the ones that they have. They have in stock building compounds. I don't want them to I want the ones that are in stock. So shouldn't have checked that. I'm gonna check this. The ones that I don't want, I want to uncheck is the one that says synthesis because it means that they want to make it they will make it, and it will take a lot of time and money. So I want in-stock building blocks, in-stock screening compounds, and then inner mine made. So let's uncheck synthesis, right? And it's going to give me almost 1,000 molecules, right? It's a lot of molecules. And guess what? I'm just going to export them, right? So I'm going to make my own library of molecules that look like my molecule. So now let's actually, because this is an exercise, let's only just check in stock screening compounds. So I'm gonna uncheck this one so that we get a smaller library for demonstration purposes, right? So I am going to, on top here, export. And when you export, we're going to export as an Excel file and also as an SDF. Why? Because Excel is going to give me the text information, and then SDF is going to give me the 3D structure information, right? That's it. That's it. And if you can open it, it's going to tell you all of the information. Very good. And this is a very slow computer. Uh, that's why we use supercomputers to run these things. But you see this SDF folder that we just downloaded? It contains all of the molecules. So do you know what we're going to do? We're going to load this SDF folder to Pyrex to dock all of them to your protein, right? We're going to dock all of them to your protein. So what you're going to do is you're going to take the protein that you already have, that you already used to dock your original molecules, right? And then you're going to dock your new library to it, right? So for the three molecules that you have found that already bound to your protein, I want you to go ahead and find three libraries, three libraries that are each similar to each of the three, right? So you're gonna get three libraries of molecules of about 300 to 500 each, and then you're going to use Pyrex to run them against your protein. So you're going to run another docking molecule, and as you can see, look, this is a list of the smiles that we just downloaded, right? So this is a list of smiles. But again, in addition to these smiles of our library, they they are gonna correspond to the SDFs, right? So what I want you to do is, again, go ahead and take your top three molecules that you already docked and you know that they bind to your protein. Go ahead and find similar molecules. Do a similarity search. And for this exercise, we're going to use ChemSpace, but do a similarity search, right? For these three. And then from this, you're going to have three libraries. And in those libraries, you're going to download them as SDF and run them against your protein in Pyrex, and then export the results. And then we're going to analyze them, and then we're going to upload them, right? And hopefully, just hopefully, you're going to find a new molecule that binds better than the original one. That's drug discovery. At least that's one part of drug discovery. Another part that I want to emphasize, right, is yes, you can do a similarity search. That's the easiest way, right? Even easier, if you do a similarity search on the FDA approved drugs, guess what's called? That is called drug repurposing, right? Because if it's already approved to treat one disease, you can repurpose it to treat another disease if you can actually confirm and show people that it actually is involved in this disease as well, right? So you can do that. But if it was that easy, we would be getting drugs all the time. Sometimes you have to do something called de novo synthesis, right? Meaning that you start with that molecule that you saw that it binds, but you do a similarity search, but you cannot find something similar that's better. So you make it up. It's called rational drug design, right? So you're going to take the original molecule and then you're like, okay, let me add an OH group here. Let me add a nitrogen here. Let me change this group and make it more soluble, right? So that you can see if it binds better and better. So based on the pocket, now that you know the charges and the shape of the pocket, you can come up with your own chemical and make it up, right? And it works very well. The only problem is now you're gonna have to make it in real life, and I don't know how to make it. I'm not an organic chemist, so I do not do a lot of de novo synthesis, but scientists do that. There are other methods like making a bunch of analogs, right? Finding one molecule that works, but then making a bunch of variations, right? So taking one branch and then let's add a methyl group. Let's add a halogen. Let's add an OH. Let's change this group and see what happens, right? These are analog making. There are also something called fragment-based drug discovery, where you start with smaller fragments to see if they bind to your protein, right? And then change the fragments and then build up on them until you get to a drug, right? So it's like let's try to see if these really small fragments bind somewhere and then add to them, right? That's fragment-based. So drug discovery is a big, big area, and again, if it was easy, everybody would be doing it. So I really want to emphasize that it's not just a matter of docking, right? You have to find a lot of molecules, but this is a good introduction. This is a good introduction of we have a bunch of libraries of a lot of molecules, some that exist, some that don't exist, but we now have very powerful computational tools to screen them for our targets and then take those things that we screened, test them on our protein, and then after we test them, we can analyze them. So in our next class, we are going to look at how we analyze them, not just for binding, but for drug likeness and whether or not they're going to be absorbed by your body or your brain, whether they're going to go into the cell. There are other things that we can do on a computer before we even go to making them. You can also test something called synthesizability, or how you can synthesize them, right? You can see how easy it's going to be to make them. But again, for the ones that we are doing, we're not going to make them, we are going to buy them. But that is a good introduction to chemical libraries, and virtual screening, right? So virtual screening is a bit different from docking, because docking is just binding one molecule to your protein, right, at a time. But virtual screening is binding a bunch of molecules to your protein. And this comes from how they used to do it in the past, where they would actually have to buy these molecules, right? Thousands of molecules, and they would spend months, sometimes years, just screening one at a time, screening one at a time. That's why it's called screening, right? And of course, eventually they came up with the robots and things like that. That's why we have things called high throughput screening. These are multi-million dollar robots that can do it automatically, but it still takes a while and it still takes a long time to get a hit. But now we can do virtual screening instead of physical screening, where we can use a computer and free tools on the internet. Now, it's better if you can use a desktop or a bigger computer, but you can do this on a laptop as well. But when you run like 500 molecules on Pyrex, if you use a laptop, it's going to take hours. So I recommend you run a desktop, and I usually run it like before I go to sleep and then wake up at night, wake up in the morning, and then hopefully I'll see the results, because if you haven't seen already, you know that Pyrex can give you um, some mistakes and some errors. So you come in the morning and you see that it actually ran for 1 hour and stopped, and then you're like, damn, I have to start again. But that's research. Research is not supposed to happen like that. Again, if it was easy, everybody would be doing it. But this one, you're going to submit your results, which will be a file with your molecules, and then an Excel file with the results, the docking results of all of the molecules, so that we can compare docking and see which one is better and how good it is. But that is it. That is enough for today. I'll see you next time.